We'll go more into detail later, as this first test is only going to be talking about waves in general. So we know that the velocity of a wave is equal to the frequency times the wavelength. For electromagnetic waves, EM for short, they travel at constant speed in a vacuum. In a vacuum, the speed of light is exactly 299,792,458 meters per second. This is exact because we define the units of meters and seconds so that this number is exact. We will approximate it, however, as 3 times 10 to the 8 meters per second. And we set this number to be the letter C because it's a constant. Thus, we can change our formula for light to be C is equal to frequency of light times the wavelength of light. And note that this is only true for a vacuum. Whenever light goes into water or glass or any other material, it actually slows down. Again, we'll learn that a little later on. Go into detail about that. But for air and a vacuum, it's basically equal to 3 times 10 to the 8. It doesn't slow down much in air or gas, and as long as we're not underwater, it doesn't really change much either on Earth whenever we're seeing it through normal atmosphere. Let's look at a very common. Also, all these light that you see, so light can be a photon. So light is both a wave and a particle. A particle of light is known as a photon. And when light is a wave, it's known as an electromagnetic wave. This is the wave-particle duality theorem. It can be treated as both. Basically, when we're observing light, it acts as a particle, and when it's moving from one location to another, it acts as a wave. We have various spectrums of light. Looking at the lowest frequency, we have radio waves. We have, after radio waves, is microwaves. Sometimes microwaves are called radio waves too, or high energy radio waves. Sometimes they'll still call microwaves radio. This is a spectrum, and there's no single point. It's blurry between them. Then after that, we have infrared. Then after that, we have visible. This is the only part of the EM spectrum we can see. After that, we have UV light, ultraviolet light. Then after that, we have X-ray, and then gamma. These are all the same thing. They're all light. It's just that we can only see visible light. They're all the exact same thing. The only difference between them is their frequencies and their wavelengths and their energies. Let's look at microwave. Haven't we already done that? Looked at. Did I take a bowl of cheese or a plate of cheese and do that? I called. So, in your microwave oven, it produces light. It produces microwaves at a frequency that is 2.45 gigahertz. Written in scientific notation, that is 2.45. The giga is times 10 to the 9th hertz. What is the wavelength of this light? Well, we can assume that it's in a vacuum or air, and in air, we have the speed. So we have the speed of light is equal to the frequency of light times wavelength of light. So if we're trying to solve for wavelength, wavelength is thus equal to C over F. C is approximately 3 times 10 to the 8 meters per second. And the frequency is 2.45 times 10 to the 9th hertz per second, and hertz cancel each other out, giving us just meters. And we get the wavelength is 0.12244. Actually, I'll write that as a 5 meters, which is the same thing as 12.245 centimeters. So to draw this scale, six and a quarter. And we have 12. $18.4. This is the true size of a microwave inside your oven. The wavelength, the distance from here to here, is 12.245 centimeters, or 0.12245 meters. So, one wavelength is approximately half a piece of paper across, a little over half. It also produces standing waves. When it hits the side of the wall, it will bounce backward. And so, depending on the shape of your microwave, you might see half a wavelength right here. But where do you think food heats up the most at? At the antinodes. So your food is primarily going to heat up right here. Right here, it doesn't even heat up at all. Here, it doesn't heat up at all. And here, it's going to heat up the most. Here, it's going to heat up the most. And in this region right here, it's not going to heat up much at all. Again, it's more blurry than this. Might go on. Have you ever used a microwave without a turntable on the bottom? With your food rotating? So when I was growing up, we had one of those without a turntable. Do you know how you cook food? You know how you cook a Hot Pocket? So instructions would say cook for 2 minutes. So what you did was you put it in for 30 seconds, stop the oven, and then randomly choose a new place and hope you chose the correct place so that it would start hitting a different spot of it. You do it for another 30 seconds, and you repeat this. If you're lucky, you have a fully cooked Hot Pocket. If you're unlucky, you have lava on one spot and ice on the other. Because the microwave doesn't cook everywhere at once. That's the reason why it's constantly turning. Because it only does at the highest peaks. If your microwave is done to offset this, you might still get more cold spots, or if it's not perfectly reflected back like this, if it is perfectly reflected back, you'll definitely have cold spots that never get heated. You might end up seeing more. Well, regardless, it's going to heat like this anyway. Even if it's not reflected back, but you might measure worse. You might see a cold spot here and a cold spot here, or you might see a cold spot here, a cold spot here, and cold spot here. This middle cold spot might not be there, depending on the shape of your microwave, because if it reflects back and not, but you'll definitely have at least 2 cold spots that are 12.245 centimeters away. And if I had some cheese, I would go ahead and do that. Hello? All right. I need you back at the office, Carlos. But you can take and remove your turntable, sprinkle in some shredded cheese, put it in for about 10 seconds, 10 or 15. 10 or 15 is probably too long. And you'll see the cheese start boiling here, and not even melted at all here. Do you know why? Do you know how microwaves heat your food up? Turn it on and get done. So you have a water molecule, and it's bent. Imagine you're on a swing set. You're on a swing set, and someone is pushing you. When should they push you to make you go higher and higher and higher? Yeah, so when you swing back here at this highest point, if someone were to push you at that right moment when you get to the back, then you're going to have more energy when you swing back forward, so you're going to swing higher up. Then when you swing back, you'll be at a slightly higher point. And if they push you again at the right moment, you'll swing back to a higher point because they're adding some energy into you and gravity's pulling you down. These hydrogen atoms are constantly bouncing back and forth. There has a certain resonating frequency. We've already talked about resonance. Like a wine glass. If you tap a wine glass, you'll hear it ringing. It has a certain frequency that it wants to ring at. And if you pump in if you add a frequency at the resonant frequency, then it's going to amplify itself. The resonating frequency of water, let me actually look it up. Resonating frequency of water molecule. Is about 2.4 gigahertz. Which is ever so slightly off from this number. Your microwave doesn't tune to the exact resonant frequency, but it's close enough that when you constantly send microwaves to this, these have electrons and protons. So electromagnetic waves interact with the electric forces, and when you send this wave, you're basically causing it to rock back and forth. And the more energy you pump into it, it gets bigger and bigger. And what is temperature? The average kinetic energy. So the faster these vibrate back and forth, the hotter it gets. Why is this number different than the resonant frequency here. Why would you not want to do the true frequency? Let's imagine you have a steak. And I don't know why you would do it, but you're microwaving it to cook it. You're sending in microwaves into it. Which portion of the steak do you think is going to heat up first? The outside layer. Now, if we had this tuned perfectly to the resonating frequency of water, what is going to happen first? The outside is going to get hotter and hotter and hotter and hotter before the cold side heats up. Now, what would happen if you're on a swing and you're still moving this way and someone pushes you? They'll slow you down. Some of the microwaves actually make the steak colder. Depending on where you are in the cycle, microwaves can actually be used to freeze things. Now, again, the true frequency of the microwave is 2.45, but they want to vibrate at 2.4 roughly. So every now and then, the microwaves will slow it down, which will allow some microwaves to penetrate down to the inside. In fact, the hotter and hotter something gets, the more likely it is that this is going to slow it down rather than speed it up. But if we had it perfectly tuned, you would never be able to cook the inside of food. It would always boil the surface before the inside even cooks. That's why we have it slightly offset. The coldest temperatures in the universe was actually man-made, and do you all know how we did it? Lasers. Very high-powered lasers that have a lot of energy. Basically, we would detect the particle moving to the left, so we shine a laser to it, which causes it to flip direction. But now it's moving at a slower speed to the right. We detect it, we send another wave in this direction, and now it's moving ever so slightly to the left. And we keep adjusting the lasers and keep matching it until we stop the atom. We can't perfectly stop it, but we can cool it off like that. What's your favorite radio station? What's a common one you've heard of though? 95.5, so FM. And this is in megahertz. So 95.5 megahertz. That's what this number corresponds to. It corresponds to the frequency in megahertz. So that has a frequency of 95.5 times 10 to the 6 hertz. What is the wavelength of microwave or radio waves?
3 times 10 to the 8. So 95.5 times 10 to the 6.
Exactly. So the wavelength is equal to the speed of light divided by the frequency. And this has a wavelength of 3.14136 meters. So a little over 3 of these meter sticks. Where is it? that color right there. This color is exactly, or roughly, 532 times 10 to the negative 9 meters. This has a wavelength of screen light. This is, since it's a laser, it's only one frequency of light. What would the frequency of this light be?
Would be the constant over the wavelength.
Mm-hmm. So 3 times 10 to the 9, negative 9. Go get this right here in a second. 3 times 10 to the 8 meters per second divided by 532 times 10 to the negative 9 meters. Meters and meters cancel out, giving us a per second, and a per second is equal to hertz. Which is 5.639 times 10 to the 14 hertz. So it's oscillating the electromagnetic field by, what's the terahertz? It's 10 to the 12, right? Yeah, 10 to the 12. Which is roughly 563.9 times 10 to the 12 hertz, or 563.9 terahertz. So that's a very large number. Visible light oscillates very fast and has actually a very small wavelength. Let's see if I can find a picture. Close enough. The wavelength of, and again, it's over a large range. So radio waves is anything larger than a meter. Anything bigger than U is going to be a radio wave. Microwaves are in the centimeters. Infrared is about the size of a pinhead. Very tiny. Visible light is on the order of cells. Actually smaller than like your common cells, almost viruses. Ultraviolet is on the size of molecules. X-ray is on the order of atoms. We actually use X-rays to figure out the crystal structure of molecules, as we can figure out how the individual atoms are arranged by sending X-rays and looking at the diffraction pattern. And gamma rays are the most tiniest. They have atomic nuclei sized or smaller wavelengths. So I don't have it on the current test. I'm probably going to change that. There's one other thing I want to talk about. The energy of light. So the energy of a photon is equal to Planck's constant times the frequency of light. is sometimes Americanized to Planck. I actually say it both ways. But it's equal to 6.626 times 10 to the negative 34. What's the best units to use? Well, we know it's going to have to give us joules. And it's going to be joules times seconds. Because the seconds times hertz are going to cancel each other out. Joule seconds is probably the best units to use. So let's look at my laser. My laser has a wavelength, and it's very bizarre that they use wavelength to do lasers. Frequency is the best unit to use. Whenever light enters water, the wavelength changes, but the frequency stays the same. But it's 532 times 10 to the negative 9 meters, or 532 nanometer light. We need to get frequency. So we can actually replace this. E equals, we know frequency is equal to C over wavelength. So we can also write this equation as HC divided by wavelength. So that would be 6.626 times 10 to the negative 34 joule seconds times 3 times 10 to the 8 meters per second divided by 532 nanometers. And every photon coming out of this laser has 3.736 5 times 10 to the negative 19 joules. A very small amount of energy, but there's a lot of energy coming out of this laser. I believe this is a 5 milliwatt laser. Legally, that's what it's supposed to be. You can't get anything over 5 milliwatts legally without special precautions. You have to get like a light, you have to, I don't know, it's not supposed to be, consumers, there's ways you can get powerful lasers, but this is 5 milliwatt is what they consider relatively safe. Do you know what relatively safe means?
Not fully safe. Not fully defense.
So, I wonder if this will actually. So, if I were to shine this into your eye, this will most definitely blind you. You'll be permanently blind. However, the moment it enters your eye, your pain receptors are going to go off before your brain even realizes it, and the nerves around your eyelids will immediately recognize the pain. It doesn't even reach your brain yet. Before you even feel the pain, your eyes are going to automatically close. And that means that by the time this enters your eye, your automatic nervous system will immediately close your eyes, and it doesn't have enough time to cause permanent blindness. Your body will actually close your eyes for you in the time before the time it actually causes permanent damage. Now, if you hold it open and force yourself and endure the pain, you will be permanently blind. Yeah. Those things are, if you were to stare at right now, you'll be blind. If it's able to burn stuff and stuff. Yeah, you would actually start destroying your vision. If it accidentally reflects off of anything, a fraction of a second before you even realize that you're blind. You shouldn't play without specialized goggles. I'm too scared to use them. Because I don't trust that I'd find the right goggles for it. It's very dangerous. Like if I were to hit the metal and it just reflects perfectly off, the amount of time it takes for it to completely blind yourself is faster than you realize. That's why these are considered relatively safe, because you have to intentionally stare into the laser to blanket blind yourself. But anyway, power. Let's look up power. Power is so this weight, a laser is 0.005 watts. A watt is how much energy per second, right? Yeah, so that's the same thing as 0.005 joules per second. And this is joules per photons. If I wanted to figure out how many photons are coming out, then I want to do per second. So what I do is do some dimensional analysis. So I have joules per 1 second. I'm going to multiply it by 3.7365 times 10 to the negative 19 joules per photon. Joules divided by joules cancel each other out, and now I'll have photon per second. So 0.005 divided by that number tells me that my laser is producing 1.338 times 10 to the 16 photons per second. And that's a lot of photons every second. Let's do a question like this. An observer measures 25 waves. Our observer sees that 25 waves fit in a 100-meter long dock. He notes that one wave oscillates up and down at a rate of 10 up-down motions per 5 seconds. What is the velocity? What is the wavelength? And what is the frequency? Or what is the frequency and what is the wavelength?
Oh, you want us
Mm-hmm.
one wavelength is 4 meters.
So we have 100 meters per 25 waves. So that would give you 4 meters per wavelength, or per wave.
That would be 2 up down per second.
So again, frequency is measured in hertz, which is per second. So this is 10 cycles per 5 seconds. Up, down motions, oscillations, cycles is fictitious. So this is 2, 10 divided by 5. And a per second is the same thing as a hertz. So 10 over 5. So if you do 10 cycles per 5 seconds, so 2 hertz means you have 2 cycles per second. And a cycle is a complete up and down motion where it repeats itself. So that's really just 2 hertz is the equivalent of 2 divided by a second. And there's a fictitious 1 second. It's 2 per 1 second. And then what would the velocity or wave speed? 8 meters per second. So if you wanted to figure out how fast a water wave is moving, if you want to be very precise while guesstimating, if you can easily guesstimate what if you knew what a football field was, then you can look out 100 yards, estimate what 100 yards is, try your best, or take a picture, calculate how many waves you see, and it's very hard for you to guesstimate a true second. So what you could do is time it for 30 seconds. The longer you wait and the more you count, the more accurate you get. For example, if it looks like it's oscillating up and down once per second, you look at your clock and you see that sometimes you measure 0.9, sometimes you measure 1.1. You're not very accurate because it's very hard for you to measure 1 second precisely. But it's very easy for you to measure 30 seconds. You might be off by 1 second, but it should be easy. And here, if you count and see that you see 28 oscillations, then you can quite easily do 28 divided by 30. And get a value of 0.93 carried. If you're off by 1 second, so 28 divided by 29, your range would go from, or let me do it the other way first, 31. You see 0.903, and then if you're off by 1 second in the other way, 0.9655. And their number is very accurate. Versus if you do 0.9, you're like way off. If you estimated the 0.1 in another direction. I'm looking at the test. This first test is very easy. I give it so that people can pass the 6 weeks. Because the next 2 tests are way more difficult over waves. So I'm thinking of a test tomorrow. Know your parts of a wave. What's the difference between a crest and a trough? A wavelength and amplitude. Know the difference between a transverse versus a longitudinal wave. Like for example, a transverse wave, the particles move perpendicular to the motion of the wave. A longitudinal wave, they move parallel. In a longitudinal wave, we have rarefactions and compressions instead of crests and troughs. Know the difference doesn't look like. What do waves carry or transport? Energy. We briefly talked about a pendulum. What does the period of a pendulum depend on? The length. What about mass? No. Acceleration of gravity doesn't depend on mass. What happens whenever a crest and a crest meet each other? That's called constructive interference. And when I'm doing like 3D, or 2D, I mean, I'll label it. So I could label, this one would be crest, and the dashed lines are troughs. And anywhere you see a crest and a trough meet, that's constructive. And anywhere you see a crest and a trough meet, that's deconstructive. So the crest and the trough meeting at the same place is deconstructive. You'll need to memorize the wave equation. V equals F times lambda. There's a lot of problems we'll ask you to solve it. I highly recommend you look at the PowerPoint. A lot of the questions come from the PowerPoint. Recall that definition of frequency. Frequency is just how many times per second. Technically, how many times per unit time. But we usually use our seconds as our time unit. I would also remember that distance, that speed, is equal to distance over time. For example, if I stated you see a wave move a distance of 10 meters in 2 seconds, you should know that this wave has a velocity of 5 meters per second. I do give a lot of weird wave equation, things like that in questions, to where for example, in this problem here, I stated that 25 waves fit in a 100-meter long dock. You should be able to recognize that we need meters on the numerator, and that waves is not a real unit. So 100 meters per 25 waves is the same thing as 4 meters per 1 wave. And the wavelength is the length of 1 wave. So even if we have a train or series, the wavelength is only for 1 wave. This was for 100 meters per 25 waves. You can simplify it down to 1 wave. And oscillations, frequencies, you should be able to recognize that. 10 up and down motions per 5 seconds. This is your frequency. You should know period. So they're inverses of each other. Period is the time it takes for something to happen. Period is just 1 over frequency, and frequency is 1 over period. So 2 hertz means that the 0.5 seconds. Everyone comfortable for our test tomorrow? Alright. Seems like a very easy test.